All right, this video is going to follow with more examples about applied optimization. Let's look at this one. So we have a rectangle that is going to be inscribed inside of a semicircle of radius 2. We want to know the largest area the rectangle can have and what are the dimensions of that rectangle. So we'll always start by drawing ourselves a picture to sort of get an idea of what's happening here. I'm going to inscribe this rectangle inside of a semicircle using my coordinate plane. So I'm going to draw my y-axis, my x-axis, and I have a radius 2, so I'm going to go up 2 everywhere. And since it is a semicircle, I'm just going to stick it here in the first and second quadrants. So there's my lopsided semicircle. And I'm inscribing a rectangle inside of this, so what I can think is I've got some rectangle inside here. There's one possible rectangle that's going to represent what's going on. You know, I could also have like a really short rectangle or a taller rectangle, something like that. But that's kind of the idea. I'm inscribing this rectangle inside of here, and I want to make the rectangle with the largest possible area. So I'm going to take away those last couple and just use this as my representative rectangle. All right, some things to note. I'm going to let this distance be my x, and this distance is my y, which is sort of what you would expect because those are in my coordinate plane. And that's going to help me come up with an equation to maximize. All right, so I drew my picture. So second, again, I need to maximize volume. So I'm going to state that as my goal. Goal is to maximize volume. Oh, sorry, not volume. What am I saying? Area. Maximize area. This is a two-dimensional thing. So what is the area of this rectangle? So the area is, length times width, but it looks like it would be 2x times y because I've centered it as symmetric. So this other length here is x as well. So 2x times y is my area. Okay. Unfortunately, that has two variables, so we are going to have to try to get rid of one. So step 3, we'll get rid of a variable, or get to one variable. And I'm going to do that by writing the equation of this semicircle. So what I can think about is the circle, think if I were to extend it down here and write the equation of the whole circle, it is x squared plus y squared equals 4. And because remember, x squared plus y squared equals 4, that's centered at the origin 0, 0. So we don't have x plus something squared or y plus something squared. And 4 is our radius squared. And our radius here is 2, because we were told we have a semicircle of radius 2. So there it is. I'm going to take this and solve it for y. So I have y squared is 4 minus x squared. And if I take the square root of both sides, I have y is plus or minus the square root of 4 minus x squared. But I'm really only concerned with the top half of that semicircle, so I'm just going to use y equals the square root of 4 minus x squared, because this is the top half. There we go. So that is the equation of this semicircle right here. It is y equals the square root of 4 minus x squared, and that relates our x and y together. So why is that helpful? I can go back over here to my area equation, and instead of saying 2xy, I can say 2x square root of 4 minus x squared. And now notice I am down to one variable, which is what I want it to be. Okay, so next I want to find my domain, and it's always nice if we can get a closed interval. We do have a continuous function. It'd be nice to have a closed interval here. So let's think, what are the valid values for x? Okay, well, first of all, x needs to be positive. And why do we want x to be positive? What we can think about is we want x to be defined as the distance from here to here. That's moving in that positive direction. X is going to be positive. We also want y to be positive, not negative. We don't want to go down here. So if y is positive, that means the square root of 4 minus x squared is positive or 0, which means 4 minus x squared is greater than or equal to 0, which means x squared is less than or equal to 4, or we can think that means that x is less than or equal to 2, but bigger than or equal to negative 2, if x squared has to be less than or equal to 4. So putting these things together, if x has to be greater than or equal to 0, and it has to be between negative 2 and 2, putting all that together says our interval is 0 to 2. It kind of restricts, if you will, x has to be less than or equal to 2 and bigger than or equal to 0. So this is nice because we have a continuous function on a closed interval, which means we can use our extreme value theorem to find the absolute maximum area. Notice we don't really care about the minimum. We care about the maximum in this case. So step 5, we will optimize. So what does that mean? We need the derivative. And once we find the derivative, we will find the critical points. One quick step, I'm going to come back up here to a, and I'm going to write 2x times 4 minus x squared to the half power. And that just helps me a little bit because when I'm about to take that derivative. All right, so let's find this derivative. So area prime, I see a product rule situation happening here. So I see like a 2x and a 4 minus x to the 1/2. So I have a product rule, and then on this right-hand term, when I take its derivative, I'm going to need a chain rule. So I have a chain inside of a product. All right. So I'll take the derivative of that first one. Derivative of 2x is 2. Leave the other one alone, 4 minus x squared to the 1/2. Plus, leave 2x alone and take the derivative of the other. So that is what? 1/2. 4 minus x squared to the negative 1/2 times the derivative of the inside, negative 2x. All right. Now we just need to clean this up so we can find those critical points. Let's see. I see a 2 here that I can cancel with that 1/2, and that makes things a little bit better. And then after that, I think I'm just going to do some factoring. So I can pull a 2 out of both pieces and a 4 minus x squared to the negative 1/2. And when I do that, I'm going to be left with 4 minus x squared on the left side, plus, I think it's going to be a minus. Let's erase that. Minus, because that negative right here. Pull that 2 out, pull the 4 minus x squared to the negative 1/2 out, and I'm left with just x times x, so x squared. So clean up another step, 2 times 4 minus x squared to the negative 1/2 times 4 minus 2x squared. And let's see, I'm going to rewrite this as 2. I see right there I can factor a 2 out, so I'm just going to go ahead and do that. If I factor that 2 out, that actually is going to make that a 4. So 4 times 2 minus x squared over the square root of 4 minus x squared. Okay. So now I want to look for my critical points. Where does this equal 0? I want to get those from where the numerator equals 0. So if I think setting the numerator equal to 0, I don't have to worry about that constant 4 multiplied in, and just look at the 2 minus x squared itself as a factor. This tells me that x squared is 2, so x is plus or minus the square root of 2. So I have plus or minus square root 2. And then where is this undefined? If I look at the denominator, what could I plug in here to make this undefined? And that would be a 2 or a negative 2. Oops. Sorry about that. Plus or minus 2. Okay, so I have 4 critical points. However, I'm not going to use them all because some of them aren't in my domain. Notice the negatives in each case are outside of my domain, so I'm only going to deal with the positive square root of 2 and the positive 2. And then I make sure I have my endpoints as well, 0 and 2. So what are my values? For x, I have 0 as an endpoint. I have square root of 2 as a critical point, and I have 2, which was an endpoint and a critical point. And I'm going to plug these into my area equation and see which one gives me the biggest value. The one that gives me the biggest value is going to be what my x value should be when I maximize my area. So if I plug these in, remember I'm going back up to my original right here, A. If I plug in a 0, I'm going to get 0 back, because think about what that is saying. If x is 0, that means you don't move out any, so you can't create a rectangle if you don't go out any on your x-axis. So area 0. Same kind of idea if x is 2. Notice it's going to cancel out this term right here and make this a 0 as well. And think about what happens there. If you go all the way out to 2, well, then you can't go up any, because if you're going to be inscribed inside of that circle. So that's also an area of 0. So it looks like our absolute max is probably going to take place at that square root of 2, but we want to check it and make sure, just to be sure. So that'll be what? 2 times square root of 2 times the square root of, well, 4 minus x squared. So that's 4 minus square root of 2 squared. So 4 minus 2. So we'll get a 2. And then 2 times the square root of 2 times the square root of 2 is a 4. Okay. So I am seeing, this absolute max is happening here. Oops, that didn't highlight very well. Let's highlight it a little bit bigger. There we go. So that is where our absolute max is happening. So let's make sure we go back and answer the questions that we were actually asked. The first thing says, what is the largest area the rectangle can have? So the maximum area, that is 4 square units. We weren't given the actual units, inches, feet, whatever. We weren't given the units, so we'll just say square units. And then the second thing is, what are the dimensions? Well, we found the x value was square root of 2. Square root of 2 is the x when the maximum area happens. To get the y, we can just come back up here where we solve for y. So that would be y equals the square root of 4 minus, well, let's see, what was my x? Oh, square root of 2. Plug in the square root of 2 right here. So square root of 2 squared is 2. So this is square root of 2. So my x equals square root of 2 and my y equals square root of 2. However, I just want to be careful. Notice my x is only half of the size of the rectangle. So the rectangle is actually 2 square root of 2 by square root of 2. Sorry, I know that's getting kind of squished in over there. But there we go. The dimensions of that rectangle would be 2 square root of 2 by square root of 2. All right, let's look at another example. Let's find the dimensions of a rectangle that has a perimeter of 100 meters, but has the maximum area. Okay, so let's draw a picture to get started. So we have a rectangle that we're given. Oops, that looks more like a trapezoid. Let's try again. Okay, close enough. So here's our rectangle, and we'll say that this is side y. Oops. This is side y and that's side x. It doesn't really matter how you label, just pick a way and label it, okay? So there's our drawing. So the second thing, let's figure out our goal. Our goal here is to have a maximum area. So our goal is to maximize area. And as we look at that, an area equation to represent this situation would just be x times y, since this is a rectangle. Okay, so as we look at that, we have too many variables. It would be helpful to get rid of the x or get rid of the y. So I need some sort of constraint. So I need to get it to one variable. And I'll use a constraint or a secondary equation. And my secondary equation here is going to come in helpful by using this idea that the perimeter is 100 meters. So that is my constraint. My perimeter is 100 meters. I only have 100 meters of, I don't know, maybe this is a fence we need to build. So fencing, we have 100 meters of fencing, and we're trying to make a maximum area out in a field or something like that. But what we have is 100 meters to deal with. So that 100 meters has to be the 2x plus the 2y, because that would be the perimeter of this rectangle. This is a little different from the one we were fencing next to a stream that we talked about. Fencing next to a stream, we didn't necessarily need fencing along the stream side of the rectangle, but here we need to include all 4. So if I want to replace that y, I can solve for y. that would be what? 100 minus 2x is 2y. So y equals 50 minus x when we divide through by 2. So I can come over here and rewrite my area equation. Instead of x times y, it's x times 50 minus x. And because I know I'm going to take a derivative in a minute, I'm going to go ahead and set this guy up nicely for a derivative. It's a quick multiplying out, better than doing the product rule in that situation. All right, so we've got this thing in one variable now. Let's find a domain. So, this is a rectangle that has to have some sort of area. So our x needs to be greater than or equal to 0, and our y needs to be greater than or equal to 0. We're in terms of x's, so we can leave the x, but for y, we would say 50 minus x is greater than or equal to 0, because remember, that's what we just found y to equal. And so what does that tell us? Rearrange, and that says that x has to be less than or equal to 50. So x has to be greater than or equal to 0, but less than or equal to 50. That tells me I have the interval 0 to 50. So I have a continuous function. I'm definitely continuous because we see that that's just a polynomial. And I've got a closed interval. I can use the extreme value theorem to help me here. All right, so step 5, I'm going to optimize. And particularly, I'm optimizing area, so I'm going to take the derivative of my area equation. So area prime is 50 minus 2x. That was a quick derivative. It's never undefined, but I can quickly set it equal to 0. And that tells me that 50 is 2x, or x is 25. So my only critical point is 25. So let's look. I have the critical point of 25 to check, and I have the endpoints of 0 and 50 to check. And then I'm going to plug those back into my area equation, either this one or this one, multiplied out or not. And I'm going to see what the area would be if those are my x distances of my rectangle. So if I plug in a 0 back to my original, well, that's just going to cancel everything out, whichever one you look at. And that kind of makes sense. If, this distance is 0 up here in the rectangle, then for sure I'm not going to be able to enclose any area. The same thing, if the x distance is 50, well, then you would use 50 here and 50 here, and you wouldn't have anything left over for y. So y, that would cause y to be 0, so the area would be 0. So again, it looks kind of like the answer is going to be here at 25 at this critical point, but we want to check and see exactly what is happening. So what is the area there? I'm going to plug it into this one here. Just quickly multiply. So that'd be 25 times 50 minus 25. So 25 times 25 is 625, and that would be square meters. So there we go. There is our maximum area right there. And let's go back and see what the question asked us to do. It said find the dimensions of the rectangle with the perimeter 100 that has maximum area. So I know the maximum area is 625. I need the dimensions. So in this case, the dimensions are x by y. Well, I know my x is 25 meters. I just found that. And my y, I'm going to come back up here. I know that y is always 50 minus x. So 50 minus 25 is 25. So 25 meters by 25 meters. So if you're given 100 meters to work with as a perimeter, maybe you can think of it again as like a fencing amount, and you want to build a rectangle with maximum area, it turns out you should build a square, right? Because we see that our x and our y match each other. All right. So now let's do something a little bit different. Let's define the dimensions of a rectangle that we know the area is constrained. It has to be 1,000 square meters, but we want to do the smallest perimeter possible. So we have a certain area to achieve, but we want to use the least amount of fencing is a way to think about it. The fencing is kind of like the perimeter idea. Okay, so again, let's draw a picture. So we draw a rectangle. Didn't quite close it in. There we go. And, we have a side X and a side Y. Doesn't matter which is which, but there's our rectangle. And our second thing is we need to figure out our goal. And our goal here is different. Last time we were trying to maximize area, but now we want to minimize perimeter. So when we write our equation, perimeter is 2x plus 2y. Okay, so be careful there. You know, both of this problem and the last problem both had to do with perimeter and area, but the equation that you optimized was different in each one because you're asked to do different things. Last time, let's go back and look real quick. You know, our goal was to maximize area, so we used the area equation, and that's the one we took the derivative of. That's the one we substituted in and everything. Now we want to minimize perimeter, so perimeter is going to be our primary equation. And we're probably going to use this area idea to substitute in and get down to one variable. Okay, so let's do that now. Let's get to one variable. Running out of room, barely squeeze that in. So what do I know? I know the area is 1,000, so area, which is 1,000 meters squared. And what is the area of this rectangle? Well, it would be x times y. So that gives me a constraint equation, our secondary equation, and it's going to help me plug into that first one to get it down to one variable. I'm just going to solve for y. So y is 1,000 over x. You could solve for x too. If you solve for x, then when you plug back in over here, you'll just have everything in terms of y and do all your derivatives in terms of y. It doesn't really matter in this case because I see either one of them is very easy to solve for. In general, pick the one that's the easiest to solve for and solve for it to plug it into the original. Okay, so what do I get? Perimeter, it's not 2x plus 2y anymore. It's 2x plus 2 times 1,000 over x. Or 2x plus 2,000 over x. And instead of over x, I'm going to say x to the negative 1 power. I know I'm about to take a derivative. That just puts it in a nicer form for me to deal with a derivative here in a few minutes. Okay, so next I want to think about a domain. Okay, well clearly my x needs to be positive and my y needs to be positive. Okay, and if y is positive, that tells me that 1,000 over x, oops, that doesn't look like an x, has to be greater than or equal to 0, which is a little frustrating here because you can think like that's always going to be true no matter what you plug in. It doesn't give us a nice boundary. You know, if you tried to multiply both sides by x, then you're going to get 1,000 is greater than or equal to 0. That's always true. You can also think about 1,000 divided by x. Well, we know x is always positive or 0. If this is always a positive number, then we're always greater than 0. We don't have to worry about having a negative. So the problem here is we're not getting an upper bound established, which means we're going to have to use slightly different method for the finding the max or the min. We don't have the extreme value theorem anymore. We have a continuous function, but no longer a closed interval. So we're going to have to figure out this using sort of some different methods than the extreme value theorem. Okay. So step 5, we need to optimize. So I need my derivative. So p prime would be 2 minus 2,000 x to the negative 2. Okay. Or 2 minus 2,000 over x squared. Okay. This is undefined when x is 0. And then when does it equal 0? We'll set it equal to 0 real quick. 0 equals 2 minus 2,000 over x squared. And I'll get a common denominator real quick. So that says 2x squared minus 2,000 over x squared. Notice you could simplify that back to my original real quick. So I would set 2x squared minus 2,000 equal to 0. That tells me that x squared, move that 2,000 over, divide by 2, x squared is 1,000. So x is technically plus or minus the square root of 1,000, but I'm dealing with a physical representation. I'm only going to deal with the positive square root of 1,000. Okay, and then just to make things a little bit easier, square root of 1,000, we think of 1,000 as 100 times 10. So this is 10 square root of 10. It's just kind of a slightly nicer way to write that. So that's our only real critical point. That and 0 is like our endpoint. So I'm going to think of this kind of like when we do that increasing, decreasing kind of idea for our relative extrema. So 10 square root of 10 can go right there, and there's 0, and that's going to go forever in that direction. And I'll do my increasing, decreasing test. Really hoping that this is a minimum, because that's my goal, to minimize perimeter, and I need to show that it is indeed a minimum and not a maximum value. Okay, so let's pick a couple things to plug in. So f prime of, I'm just going to plug in a 1. That's nice and simple to plug in. Definitely less than 10 square root of 10. And then square root of 1,000. If we do, the easiest thing to do if you're not sure what that is, just give a quick plug in your calculator, get an estimate of what that is. So the square root of 1,000, see, I know it's going to be bigger than the square root of 900, which is 30, right? So square root of 1,000 is like 31.6, just as an estimate. So I'm just going to plug in maybe like f prime of 40. That's a nice round number I could plug in. All right, so I'm plugging into my first derivative. I'm actually going to look at this factored version down here. That's always positive on the bottom. And just kind of then I need to look at my numerator. So what is that going to be? 2 times 1 squared is 2 minus 2,000 is negative. So I am decreasing here. That's good. I wanted this to be a minimum. If I plug in a 40, 40 squared is 1,600 times 2 is 3,200. When I take away 2,000, that's definitely positive. So there are no other critical points on this interval. So this is the only minimum value. It's going to increase forever after it, and it's decreasing forever before it. So 10 square root of 10 truly is a minimum, and I can be comfortable saying that. So 10 square root 10 is where the absolute minimum occurs. Okay, so let's go back and see what our question was. It says find the dimensions of the rectangle. So x, so our dimensions, x equals 10 square root of 10, and y is, well, it's 1,000 divided by x, so it would be 1,000. I'm going to come over to the side to do that. 1,000 divided by the 10 square root of 10, so that takes off that is 100 divided by the square root of 10, and maybe if we clean this up a little bit, if we don't like that, what am I trying to say? Sorry, lost my train of thought. If we don't like that radical in the denominator, we can rationalize this and make it look a little bit better. So this is 100 square root of 10. Square root of 10 times square root of 10 is, well, 10. So that knocks that off, and we get 10 square root of 10. Oh, so it's actually a square. We get 10 square root of 10. Alrighty, so there is our answer. Those are our dimensions. Okay, so here's another one. We're going to design a rectangular poster, and we want this poster to contain 100 square inches of printing. We're going to have 1-inch margins on the top and bottom, 4-inch margins on the right and the left, and we want to figure out the overall dimensions to minimize the amount of paper used. So this is sort of an example where you're minimizing like the amount of product used. You don't want to use more paper than you have to, but you have some constraints of the margins and how much printing you need to put on there. So let's draw a picture. So we have this rectangular piece of paper. Okay, I'm actually going to make that bigger. And you'll see why I'm going to make it bigger here in just a second. It's because I need to go inside of it and make, oops, the margin, so I'm going to make it really big so it's easier to see what's going on. It says that this inside needs to be 100 square inches. And the 1 inch margins on the top and the bottom. So what does that tell me? That says that this distance is 1 inch and this distance is 1 inch. And I need 4 inch margins on the right and the left. So I did not draw this to scale, but that's 4 inch and that is 4 inches. So that's sort of what I'm looking at. I'm going to print a poster that has those margins around the edges and then has something printed there on the inside that's going to take up 100 square inches of printing. Okay, so that was step 1. I drew a picture. Step 2, I want to minimize paper. That's minimize the paper used. That's going to be an area idea, right? Because this is a two-dimensional thing, so I'm minimizing that area is my goal. And the area of this, well, I mean, I can call this X and this is Y, right? That's the full area of it. So that is X times Y. Okay. I need to get that to one variable. So get to one variable. Let's think about how these are related. Well, we know what is the constraint. The constraint is we only have 100 square inches of printing. We need exactly 100 square inches of printing. So that inside area, 100, has to be, well, it's not X by Y. X by Y is the big outside part that includes the margins. I need to include this piece by this piece. And how are those related? Well, this isn't all of X. It's X, take away this margin, take away that margin. So this little piece in here is going to be X, take away 4, take away another 4. So I can think, make it another color. This is going to be X minus 8, this distance here. All right, and then, so that's X minus 8. And then times the other side, Y. It's not all of Y, it's Y minus this inch and minus that inch. So we get that this distance is Y minus 2. Okay. So that inside printed area is X minus 8 times Y minus 2. And we want to remove one of them, solve for it. I'm going to, I don't know, it doesn't really matter. I'm going to solve for Y here. I can solve for X too. It's not that big of a deal which way I choose. I'm going to solve for Y. So if I do that, I'm just going to divide both sides by the X minus 8. So 100 over X minus 8, that equals Y minus 2. So if I add the 2, that's my Y. So there is my Y, which means now I have one variable. Area of the whole big poster is X times, not Y anymore. I'm going to call it 100 over X minus 8 plus 2. Okay. And I'm going to take a derivative of this in a minute rather than doing the product rule. If I leave it like it is, I have to do a product. And inside the product, that one's going to need a quotient. That sounds kind of like a mess. So I'm going to multiply, and I get 100x over x minus 8 plus 2x. And that looks a little bit better to differentiate. All right. Now I'm going to talk about a domain. Again, you know, x has to be greater than or equal to 0, and y has to be greater than or equal to 0. Those are for sure things that has to happen because I'm making a piece of paper. That y is 100 over x minus 8 plus 2 has to be greater than or equal to 0. I end up with that. And then now I'm just going to sort of move things around and solve for x. What do I get? 100, oops, kind of running out of room down here. 100 over x minus 8 is greater than or equal to negative 2, which tells me that 100 is greater than or equal to, I'm going to multiply both sides by that x minus 8, so that'd be a negative 2x plus 16. And so that says that, move that 16 over, I got 84 is greater than or equal to negative 2x, which tells me that x divide by -2, I get a -42 over here, but I have to switch my sign around. So x is greater than or equal to -42. That's not super helpful. I already know x has to be greater than or equal to 0, and now it's told me x is greater than or equal to -42. Yeah, well, x is greater than or equal to 0 takes care of that. What I'm kind of seeing happening here is I have a lower bound, but I don't really have a true upper bound. And if you want to think about why that makes sense, this paper, you could make in it, build your margins. And this inside, if you want 100 square inches, you can make the Y infinitely large. And as large as you make it, bigger and bigger and bigger and bigger, you just squeeze this X down and let it approach a distance of 0. So where it's almost just like the longest, thinnest line you can imagine. So there is no true upper bound here. So we can't use that extreme value theorem, but that's okay. We can use our increasing, decreasing, relative extrema kind of idea to prove that what we found is indeed, what am I trying to say? A minimizing area. Any other things we see kind of as we're going? I know that also, I guess really x, instead of x being bigger than or equal to 0, really x has to be bigger than or equal to 8. Should have done that from the beginning, right? Why does x have to be at least 8? Because you have to have 4 inches on each side. And I guess y has to be at least 2. If we went through and change that, if y is at least 2, it's going to change this slightly, but let's actually do that real quick. My bad. I kind of forgot that we had some margins there that were a little bit important. All right, greater than or equal to 2. So if this is a 2 now, down here, when I move that 2 over, that's actually going to be a 0 now. So now I'm kind of getting that same idea as before. This fraction has to be bigger than or equal to 0. And I know that my x is always bigger than or equal to 8. So this thing is always positive no matter what. So actually, none of this really made too much sense. Sorry, guys. I kind of got sidetracked forgetting about that I do have that fact that y had to be greater than or equal to 2, not 0. All right, so x has to be bigger than an 8, but we don't really have an upper bound. So let's optimize now. I need my derivative. So I will need the quotient rule on that first part of a. So x minus 8 times the derivative at the top is 100 minus 100x. Derivative at the bottom is a 1. That's nice. Over x minus 8 squared plus derivative of 2x is a 2. So we need to do some cleaning up to make this look a little bit nicer. What do we get? 100x minus 800 minus 100x. Oh, that's kind of nice. Over x minus 8 squared plus 2. Those cancel, and it looks like my derivative is negative 800 over x minus 8 squared plus 2. Okay. If I want to see where does this thing equal 0, so I'm going to set it equal to 0. That tells me that, let's see, 2 equals 800 over x minus 8 squared, which tells me that x minus 8 squared equals 400. Move that 2 and divide. So I can take the square root of both sides. That tells me that x minus 8 is plus or minus the square root of 400, so that's plus or minus 20. So x minus 8 equals 20 tells me that x is 28, and x minus 8 is negative 20 tells me that x is a negative 12, which is outside my domain, so I don't worry about that. So it looks like my critical point here is 28. So I'm going to look at my line here. So what do I get? from 8 is my endpoint, 28. I want this to be minimizing, so I'm hoping I'm decreasing here and then increasing forever. And then I found like the bottom here at 28. So what do we want to check? Maybe like f prime of 20, that seems nice, and f prime of 30. Plug those in real quick and see what's happening. So f prime of 20, if I go back to my derivative, here we go, here's a derivative I can plug into. F prime of 20, because I have this added here, I can't just do my, multiply like positive times positive kind of situation, my sign analysis. I actually do need to either get a common denominator so I can use that sign analysis, or I need to just plug it in kind of like it is. I'm just gonna plug this in like it is. So what happens if I get, let's see, negative 800, I'm going to divide that by 12 squared. Oops. Except I can't type in my calculator, so I should have done this before. Negative 800 divided by 12 squared is negative 5.5-ish, 5.6, negative 5.6-ish. When I add that 2, it's still going to be negative. So this is about negative 3.6 or so, about negative 3.6. So that is decreasing. And then if I plug in a 30, I'll have negative 800 divided by 30 minus 8, so that's 22 squared. So 22 squared, and then I'm going to add 2. When I did that one, I get an answer of about 0.35, and that is positive. So I do see that I do have a negative, and I'm guaranteed there's not another negative anywhere on that interval because it increases forever after 28. So I can be guaranteed that is a minimum. I do not actually have an absolute maximum on this interval, 8 to infinity, because it increases without bound. So what is the question I was asked? Let's go back. So what overall dimensions minimize the amount of paper used? Well, X I just found should be 28, right? X needs to be 28. And then Y, how do I find Y? I just go back up here. So if I plug in a 28 right here for X minus 8, 28 minus 8 is 20. 100 over 20 is 5, plus 2 is 7. So my Y should be 7. And I guess what were these? These are in inches. So if I want to minimize the amount of paper I use, but still have 100 square inches of print with 4-inch margins on the right and left, 1-inch margins on the top and the bottom, then I should make this 28 inches by 7 inches to minimize the amount of paper I use.